Hi, this is the second video of cross entropy, but before jumping into cross entropy and gradient descent, I will briefly review the last video. First of all, I'm just giving some insight. What is linear regression and logistic regression? Linear regression is to predict by the data, and especially we are trying to make some model which work like models data's distribution. For example, if let's say this is the study hour, how much we study for exam, then it will be score. Then I can say if we study more, then of course there is some exceptions, but normally if we study more, then grade score will be higher. So we make this prediction models. But in terms of logistic regression, it is kind of classification. Therefore, there is binary or multi-classes, but in terms of logistic regression, we are classifying the binary case. Therefore, there is 0 and 1, or pass or fail, live or die. So it will be same with study hour, but because it is not some continuous value, it will be some value like 1 or 0, because it is binary case. So I will say this is pass or this is fail. Therefore, if we study until some certain time, then we will just fail. But if we study quite longer, then we can say we will pass some exam. So this will be the threshold value. Threshold. So the graph will look like there is no certain the linear graph which can draw or any line, because it's not suitable to predict this or represent this graph. Therefore, we are using sigmoid, logistic sigmoid. So logistic sigmoid looks like I will change the color like this shape, and this will be normally 0.5, and this will be the threshold value of some time. So in summary, linear regression is to represent with lines and data points, and logistic regression is for classifying for binary case. Okay, and then I will further explain about the cost function, because we need to find this blue curve which represent our data or classifying with regard to the data. So in terms of linear regression, we are using least square error, and in terms of logistic regression, we use cross entropy, and it is something learned from last video. Okay, so the shape of least square is like 1/2 y prediction. So, and our target label square. So this is our models prediction, and this is label, so ground truth. So if we can say this is answer or label or ground truth data, and models prediction is they are really close, then error will be really small, because this is always the positive sign because of a scale. So in this graph, this length of red line will be the least square error. But however, cross entropy, we cannot use this least square error, because the merit of using least square error is this function is quadratic form, so it is convex. So it's easy to find some optimum value. But because this sigmoid is non-linear, so if we use this least square error function, then this non-linear will make multi-local optima. That means it will look like this kind of shape, so we are not sure this point or this point, which point is optimal. So we have to use cross entropy. So in order to learn about cross entropy, please go back to the first video, then you will know about this. And then gradient descent. Because I said we will have a convex form by using least square error or cross entropy function. Cross entropy function will also look like this shape. So I will just draw this quadratic function. Then let's say we are here, and because this is function, I have to draw axis, and it will be w or weight or parameters. And this axis will be error. So here we are going to use Newton method. Because of the definition of derivative, if we calculate this derivative with regard to the weight, then it will be the slope. This will be the slope of this line. And our error function is here like this, quadratic form. So if we here multiply some value, then it will be x value, and then this value, if I assume this is the length of some learning rate, I will explain, then total this value will be this magnitude. Therefore, anyway, we have to move our weights toward this side. So we will say our future weight, the next iteration's weight will be current weight here minus some coefficient, some constants, and multiply round E over round W. Then we will move toward this amount. So this value will be this magnitude. Therefore, this our next value will be here. So our error will be decreased. And then here we will again will calculate some value and multiply this learning rate coefficient constant. Then we will move. So finally reach to here. If the data point were here, then I can also draw like this, because this slope will be minus, this slope will have a negative sign, therefore it will be plus, it will become plus, then it will move toward the right side, positive side, and it will in the end will reach to this maximum point. And this mechanism is called gradient descent. And here's something more efficient way, because this is quadratic form. If we just try to use a higher order in order to calculate in order to apply Newton's method, then it will be more efficient. Therefore, we would use Taylor series up to second order. So let me briefly explain about the concept of this theory. So if fxk plus t is approximated by using Taylor series and second order, then it will look like this. Right, and now we want to know how much we have to move. So we want to calculate the value t. So how long, how much I have to move in here. So I can say this is the value t in this case. So since this is quadratic form, therefore I will derivate with regard to t, then the value will be 0 and dt of this whole value equation will go here. So I just want to find some value t which makes this quadratic equation as 0. Then it will be f prime xk plus t plus f double prime, so second derivative of xk. Therefore, finally, we got it. T is equal to minus f prime xk and f double prime, so second derivative. So we have to just find this value. So in last video, I calculate this value from cross entropy as minus Tn, like this. But here, we also need to calculate this value, but it's really easy because we have already calculated and derived this equation. Therefore, it will look really simple. It will be n so here, this t value will disappear because it does not have any relationship with our derivative. Therefore, because we derivative with regard to y, this is the function of error with regard to W, to some weight parameter. So as you know, this is sigmoid W on our basis function. Therefore, sigmoid is the derivative form of sigmoid will be like this. So we have this equation, and it comes from the last one, and this equation happens when, because this basis function is the coefficient, kind of coefficient of weight, so we got it. So that means we can still calculate this second derivative of cross entropy. So alright, so we will try to find the next weight or parameter as just minus t, and here we calculate the value t, and again this t is the distance or length of this one for calculating gradient descent. Therefore it will be written as Wt minus Hessian matrix inverse. This is a general form, and H will be okay. 1 second, please. H is just from the second. H comes from the second order derivative. And this is the first order derivative, okay? The reason why I changed the form is because this is the standard form, and you will see many times this equation. So it is better to use the standard form, then you will feel more comfortable when you learn something deeper. So as I said, when we calculated linear regression, we used error function or cost function as least square error. Therefore, it was the reason why I keep comparing with linear regression is because it will help you to understand better. So the first derivative will be I will write it down as a matrix form. Okay, then Hessian matrix, which is second order derivative, will be like this. It is really simple mathematics, so I won't explain too much like this. I think you guys can understand really well about this part, but in terms of cross entropy, then it has a different shape and form. So the point that we have to realize and understand is we have only this and this equation. So if we apply this concept here, then Wt plus 1 will be Wt minus inverse. Now you can understand why I used matrix form, because it is way better to calculate this form. So because I will expand the equation, then -1 here, here will be transpose minus and -1, and sorry, the transpose will be here, and it is just inverse, so it will be cube omega t plus, I will just write it like this, because this term will be just cancelled out, because this and this are just identity equation, and this will be also identity matrix, sorry, so it will be cancelled out here. So finally, this is really amazing. T plus 1 will be just this form. That means we have a closed form solution. We can find out exactly the right graph. Like if we have here, then we will go directly to the optimum point. But this magic won't happen in cross entropy case, so I will quickly go for this one, because we already did it in the last videos, but I will quickly go over this time because it is much helpful to understand. Alright, this is the equation of cross entropy, and so then I'm going to calculate first order derivative here, and we calculated last time up to this part, and as we did, I will change it to the matrix form. And again, I will calculate Hertzian matrix, which is second derivative of error function, will be, as I explained just right before, will be this form. So I will just write down the matrix form. So it will be and here I'll and n will be y1 minus yn. I will show you once again to understand better. Oh, sorry, 1 second. We have this Hertzian matrix and this equation. It changes to this shape, and my goal is to apply this second order Newton's method. So I will apply the equations to Hertzian matrix on our first derivative equations. Then it will be this is a Hertzian matrix, and it looks like this. Therefore, here's the problem. Is R this R already contains the value of Y, so it is affected with our prediction. Therefore, we don't have no constant weighting matrix. That means, sadly, we don't have, we can't derive closed form solution. That means we can't directly go to this minimum point, but still we can, using iterative method, by moving these amounts and moving these amounts, because since the cost function is quadratic form, it is more efficient approximate with second order points. It's much better than just using the first order. You can imagine, because this is second order. If we try to use the gradient of second order, then it will move following this gradient, so it can converge faster. But there is pros and cons, because this Herschel matrix require more computational effort. Therefore, even though it is fast to converge, but it takes more computational effort. Therefore, if we have a high enough computational power, then researchers prefer this Herschel matrix. But if that's not, then we try to adjust with learning rates by just finding optimum or appropriate learning rates. We can reduce the time to find good answer. So this iterative method is just called IRLR, iterative reweight least square. I think you guys can understand from the algorithm. Okay, thank you for watching this video.